So what makes this method of Lagrange multipliers work? Or as Arnie used to say, what was Lagrange smoking? Ha ha! So here's the deal. Suppose the function that you are trying to optimize, your big F, represents the temperature in space, temperature at any point X, Y, Z in space. And let's say you have an astronaut flying in space. Colonel, I'm going to ask for a volunteer from the audience, or you'll get involuntarily volunteered. Who would like to be my colonel, my astronaut? No one is volunteering.
I would like to volunteer.
Okay, Esteban, you will be my colonel. Okay. Okay, we got Colonel Esteban here. Esteban Gomez. He's going to be our colonel. Okay, great. Thanks. Okay, so Colonel Esteban, he wants to land on planet X. And planet X's surface is represented by, you know, surface equations, like a planet might be in the shape of an egg or maybe a sphere. So we'll have some sort of equation, G, X, Y, Z equals a constant. It's some level surface, like an ellipsoid equation or something like that. And we can rearrange the equation where we subtract the constant. So we'll have G, X, Y, Z minus C equals 0. And folks, this is our constraint equation. We're constrained because we have to stay on the planet, planet X. So let's say the colonel, and that would be Colonel Esteban, he's hunting on the surface. He wants to find the point of greatest temperature on the planet. What's the hottest point on this whole planet? So let's say as he's in his little like Mars rover, you know, cruising along the surface of the planet, he notices that he finds a point where the temperature is the greatest. And so he's got his little recording device where here's the temp on the vertical axis, and here's T for time on the horizontal axis. So as he's cruising along, boom, he gets a max temp, and then if he goes away from that point, it gets cooler. So right there is the point P, max temperature. Okay. Well, Colonel Esteban is not convinced. He's like, yeah, well, you know, maybe that's the hottest point on the planet. Maybe not. So I'm going to keep cruising. And so he keeps cruising and he's on some different path. So then he finds, oh man, so here he is on the, let me just show you. Here's the surface. Let's say here's the point P. And the first path that Colonel Esteban was on, you know, he was like, let's say rolling along here. Here's the first curve, C1. He sees it's the hottest point. So he's like, I'm not buying it. Let me do a different path. So he's like doing some other path. And let's say that path also crosses over point P. We'll call this curve 2. And let's see on curve 2, he also still notices that point P is the greatest temp. You know, so the first time he recorded, this was for C1, but now he's got his recording device and he's, you know, looking here, and he still finds that that max temp, boom, is happening at point P. He's like, dang, okay, that's the peak temperature. And he keeps doing this for more and more curves, and he keeps noticing, all right, well, you know, maybe this is the hottest point on the planet. So now let's talk about the calculus involved. So what is the temperature as a function of time on either of these two paths? Remember, our function f is a function of x, y, and z in space. But suppose that x, y, and z, you know, are related to function of time. Time is driving the bus. And your vector valued function, which is also a function of time, can be given to you, and these are the paths that Colonel Esteban has taken. You can do a vector valued function for any of those curves, r of t with components x of t, y of t, z of t. So your function, big F, you can plug in x of t, y of t, z of t, since they have to still satisfy the function because you're on the curve. And this is one big mother function of time, as Dr. Vallone would say. So our first semester calculus, we know what? If you've got a peak right there at point P, what do we know? We got to have f prime of t equal to 0 at the max, which is where point P is, max temp. So using our chain rule diagram, the tree diagram, we can write out what df dt is. So f prime of t, which we can write as df dt, is going to be the partial of f with respect to x times dx dt. And be careful because some of these d's have curvy stems and some have straight up and down stems. Straight up and down if it's a function of a single variable, which x, y, and t are. And then the last term, df dz times dz dt. But this has to equal 0. Why? Because it's where the max is, right? You have a max, your derivative is 0. Yeah. Now, I want you to notice that this looks like a dot product. Something times something plus something times something plus something times something. It turns out it is a dot product of two vectors, and it's a dot product of a vector containing the partials, which happens to be the gradient of big F, dot product with a vector that contains the derivatives of x, y, and z, which happens to be the velocity vector, or r prime. And when you have a dot product of two vectors equaling 0, what can you say? So does this look like a dot product to you? Yes, it's the dot product of del F and r prime. So what's the relationship between those two vectors since the dot product is equal to 0?
Aren't they orthogonal?
Yeah. So the gradient, that's big del F, is always perpendicular or orthogonal to r prime, which is basically the tangent vector to the curve. And it's actually orthogonal to every single tangent vector, to every single curve on that planet. So we learned in a previous section that the gradient for the constraint surface, that's the big G, x, y, z, is also orthogonal to level surfaces, just because, how do you think we found tangent planes to surfaces? So in other words, the gradient of big del G is also having to be orthogonal to every tangent vector to the curves. So both big F and big G, does that mean they're equal? No, but it means that the gradient of the temperature function, that's big del F, is going to be parallel to the gradient of the constraint. In other words, del F is a multiple of del G. And that's sort of the key for Lagrange. Why? Because, you got two parallel vectors. So like, here's your planet here. Okay, here's planet X, surface. You've got a curve or any curve on there. Draw any curve you want, all the curves. Del big F is orthogonal to every single one of those curves. Fine. But del big G also has to be orthogonal to all those curves. So these guys are parallel. So that means that one is a multiple of the other. So you can write del F is equal to some multiple C times del big G. But instead of this multiple being a constant and naming it C, we name it lambda. That's all. Okay. So once again, the book will tell you that what you're doing here is you're setting the gradient of big F, that's the gradient of the function that you're optimizing, equal to lambda times the gradient of your constraint. And then after distributing your lambda, you equate the components and you get a system of equations that you need to go solve. Okay? And we're done. And that's why Lagrange multipliers work, because these two gradients are in parallel and the Lagrange multiplier is the multiple. Pretty cool, huh? I just derived the whole reason for it. I thought that was exciting. All right, so here it is officially, the way I do it. So if you're trying to optimize f, and I usually call this big F, but we could call it little f, subject to a constraint little g, I typically call it big G, where you rewrite it as big G equals 0. Then the max or min is going to occur at the critical numbers of this new big function L, the Lagrangian, which is going to be a function of 4 variables, x, y, z, and lambda. And when you form it, it's simply going to be your big F minus lambda times your big G. And then just go find the partials of big L and set them all equal to 0. And you'll solve the system. And then you'll get a critical point or critical points. Now, if you get a critical point or a critical points, how do you know if it's a max or a min? Because you're not doing the d-test. You actually find it by trial and error. Yeah, I know. You plug it in to see if it's maximizing or minimizing. Well, that seems really primitive. Yeah, but usually you know in advance what if you're looking for a max or a min. That's the point. So let's do another problem that we already know the answer to. Really? Yeah, we did example 2 last week. We did find the maximum volume of a rectangular box resting at the origin, one vertex at the origin, subject to the constraint of a plane. So I don't know if you remember this, but I claim we did this, where the box was sitting flat on the XY plane with one vertex at the origin here. Ooh, it's kind of hard to draw in 3D. And then its other vertex was located in the plane. Does anybody remember doing this problem? Yes, no, maybe. I'm going to do this problem all over again. Oh man, why? You already did it. You already know the answer. Because I claim it's easier to do it using the method of Lagrange multipliers. That's why. Yeah, I don't have to do no d-test. It's great. So we're going to do the problem all over again. And you'll see that we will get the same answer. Don't worry. So here we go. So doing it the way that I'd like you to do it. The big F, the function that we're trying to optimize, which is volume, that's x, y, z. And, I'm going to call that the big F. And then the constraint, remember, is your plane equation. Although I'm going to rewrite it where I get everything on one side and 0 on the other. So 6x plus 4y plus 3z minus 24 equals 0. So this stuff on the left, I'm going to call it big G, which is a function of x, y, and z. So now my Lagrangian, oops, I can't spell, my Lagrangian function, remember that's who I refer to as big L. Big L is a function of 4 variables. It's going to be the function you're optimizing minus lambda times your big G, your constraint. Okay? So for us, our big Lagrangian, x, y, z, lambda, is going to be the volume, x, y, z, minus lambda, that's our angel from heaven coming to help us, times parentheses 6x plus 4y plus 3z minus 24. There's your big Lagrangian. You're going to go get his critical point or points. No d-test needed, though. So you need to get 4 partials. And I want to see all this work on your handwritten stuff. I'm going to put one Lagrange method multiplier function, problem on your exam next week. Just one. Go practice. So let's take the derivative of our big Lagrangian. There he is. With respect to x. It's not as bad as you think. Well, the first term, I'm just going to get yz minus lambda times parentheses. And then the derivative of this plane equation with respect to x is just 6. Hey, that's easy. And set it equal to 0. Okay, and now go differentiate with respect to y. I get xz minus lambda times 4. Set it equal to 0. Take the Derivative of our big L with respect to z. I get xy minus lambda times 3. Set it equal to 0. Differentiate with respect to lambda now. That means hold x, y, and z constant. So, the first term's derivative is 0 minus, and I'll get the everything in parentheses because that looks like a constant, multiplying it by lambda, set it equal to 0. Keep in mind, this is our constraint. It's the same. It's our plane equation that's constraining our box from being able to grow too big. Okay, and if we tackle this problem the same way that I encourage you to do most problems, I'm going to do one that isn't in this module here, but I'm going to solve for lambda 3 times, okay? When I solve for lambda with the first equation by adding 6 lambda to both sides and then dividing by 6, I get lambda is equal to yz divided by 6. Okay, save that. I'll call that my number 1 lambda. If I solve for lambda a second time with the second partial, I get lambda is xz over 4. Call that our number 2. Solve for lambda again, and I get xy over 3. Call that our number 3. Oh my goodness. All right, now what? Well, I'm going to start setting each lambda equal to another one of the lambdas. I'm going to try to get my variables, everybody in terms of x. I always make that my command decision. Okay, you can get everybody in terms of y if y is your favorite variable. It's up to you, but make sure you pick one. You got to pick a lane. You can't be all over the place. That's a common student error. They just don't know what they're doing, and they're just like, I don't know, let's just hope it, light a candle and hope it all works out. That is not the way to tackle these. You will end up really, really disappointed and frustrated. Okay. So how about if I set number 1 equal to number 2? So my number 1 lambda was yz over 6. I'll set it equal to my number 2 lambda xz over 4. They have to be equivalent. Lambda has to equal lambda, right? Now what? Let's try to get y in terms of x. Notice that both sides have a z in it. So if you divide both sides by z, or multiply both sides by 1 over z, assuming z isn't 0, of course, and we're going to assume that because we don't want our box to have, 0 is the height. You'll get y over 6 is equal to x over 4 because the z's will cancel out. Now what? Let's solve for y, and then I multiply both sides by 6, and then let's reduce. So I get y in terms of x. Ooh, cool. Y is 3/2 x. Save that for later. Now what? I'd like to get z in terms of x. That's my next goal. So how about if we set the number 1 lambda equal to our number 3 lambda now? So I'll have yz over 6 is equal to xy over 3 and see what happens. Now notice that both of the sides of the equation have a y in it. So let's divide out by y. Cancel, cancel. And I get z over 6 is equal to x over 3. Fine. Multiply both sides by 6. And then reduce, and I get z is equal to 2x. Fantastic. I got z and y in terms of x. This is good. Both y and z are in terms of x. This is a good halfway point. If you can make it this far, you're almost there. Okay, so what are you going to do? You're going to substitute all into the constraint. Okay, now what's the constraint again? Remember, it's the plane equation. That was 6x plus 4y plus 3z equals 24. That's your constraint. You're going to let x be itself. X is just x. Because, I chose that as my lane, and everybody else is in terms of x. So I substitute 3/2 x for the y, and I'll substitute 2x for my z, and then now I have an equation in x. Yay! Solve for x. And let's do a little bit of reducing. 4 divided by 2 is 2. So this is looking like 6x plus 6x. Hey, let's add my like terms. Okay, when I add all of the x terms together, I get 18x is equal to, this is supposed to be 24, my bad. Sorry, I accidentally just wrote a 4. 18x is equal to 24, and then solve this for x. Aha! And then reduce, because these are both divisible by 6, right? and I get x is equal to 4/3, which is exactly what we got when we did this whole problem before. And since y is equal to 3/2 x, that means y is 3/2 times 4/3, and then reduce, and this looks like y is going to be a 2. And remember, z, we got z in terms of x, it was 2x, so z is going to be twice 4/3, which looks like 8/3. So the dimensions, and they didn't give us any units, we don't know if it's meters or feet, but it would be 4/3 by 2 by 8/3. And so then our max volume is simply the product of 4/3 and 2 and 8/3, which is 64/9 units cubed. And we've maximized the volume of our box subject to a constraint. And that concludes that example. So here's the example that we did last week. It was the same problem, but we did it using a completely different approach. This is last week's, okay? So how did we do this problem last week? Well, last week, we still had to maximize the volume and do the calculus on it, but we had to reduce it to a function of two variables. So we had to solve the plane equation for z, which was kind of a pain in the butt. There it is right there. And then we substituted that in place of the z in the volume equation. And that way volume was a function of x and y only. But then volume looked really horrible. And then when we had to take the partials, and then we set the partials equal to 0 and had to solve this god-awful nonlinear system of equations. Oh my goodness, and we had to do some factoring and ZPP, and then we got a critical point we ignored, and then we got a linear system, and we solved that, and we got a critical point, and then we had to do the d-test. See this d-test right here? You know, and get the second partials. And then we had to do, you know, figure out we had a max. Okay. Okay. So that was last time. So what do you guys think? Which one do you prefer, Lagrange or this way that we did last week?
I like the Lagrange a little better.
Okay, Aaron says Lagrange. There's somebody in the chat that said, I think Angel said that he said, I prefer Lagrange also. I don't know how the rest of you feel, but I prefer Lagrange myself. It's not like easy peasy, but it's easier. And that's the beauty of it. You see, that is the beauty of Lagrange. I hope that you can appreciate that. Okay, so let's do another example of Lagrange with the three variables. Okay, one we haven't done already. Yeah, okay. Here's one that I love, and I'll tell you as we're doing it why it's near and dear to my heart, and that means you may see it on a future quiz or exam. So I just get a question here. Will I specify which method that you are required to do? Good question. It depends. You may be asked to use Lagrange and you don't have a choice, like, oh, you better use Lagrange. Okay. And there may be times where the problem says, hey, use any method you prefer. Okay. And, you know, if you can use any method you prefer, of course, you probably would prefer Lagrange. Now, you can't use Lagrange all the time. When is there a time where you cannot use Lagrange? So to answer that question, I want to be very clear. You cannot use Lagrange. So here's the fact. When you lack a constraint. So you cannot use Lagrange. Although Lagrange is a great method, I love him. If you are lacking a constraint. Well, is that ever going to be the case? Yes. Okay. Well, have we done a problem where we lacked a constraint? Yes. When? I'm going to show you. Well, how about the quiz you just took? If you did take the quiz, you probably remember there was a word problem on there where you were trying to maximize profit. And profit was given by revenues minus costs. That's a very good business economics equation that you should know. There's no constraint in that word problem. There was no constraint. The profit wasn't constrained by anything. So for that problem, if they did try to trick you, and I say trick you, like, oh yeah, use any method you prefer, you couldn't even use Lagrange if you wanted to, because there's no constraint. Okay, and another example, Lagrange wouldn't even be available as an option, is last time when I was doing this profit problem here, this profit problem from last lecture, there was no constraint here at all. So you kind of get forced into using the regular method where you have to go use the D test and so on. So great question, and I hope that answered it for you.
Thank you.
Okay, now back to this problem here, which does have a constraint, so we can use Lagrange. Okay, so we've got another temperature function, the temperature on some ellipsoid. You can think of this as being planet X. We could go back to Colonel Esteban. Thanks, Colonel, for volunteering your services once again. So this would be the temperature on this big egg. You know, if you graph this ellipsoid, it'd be an ellipsoid-shaped planet, you know. So anywhere on this planet, you're going to try to find the temp greatest and the least. So you're going to try a max and a min. Cool. Can you get a max and a min? Yeah, you can. And we're going to find all the critical points and then figure out which critical points give a max and which give the min. Okay, this is a little bit tricky of a problem, but it's fun. You'll love it. Okay, so here we go. I'm going to first write the big Lagrangian function, which is L function of x, y, z, lambda, and that's going to be our temperature function. That's the one we're trying to optimize, maximize, and minimize, minus lambda times our constraint, big G. Now, who is big G? That's the planet. And I'm going to rewrite big G where everything is on one side and 0 is on the other, because that's the technique. And then get it all set equal to 0. So there's our constraint. And because we have a constraint, that means you can use Lagrange method. Otherwise, you wouldn't be allowed to. Okay, so for us, the big L, I just can't write anymore, is 8xyz minus lambda times this 16x squared plus 4y squared plus 9z squared minus 144. Okay, let's go get this guy's partials, set them all equal to 0. And try to solve a nonlinear system. So I got to go get Lx, Ly, Lz, and L lambda, all four, make it happen. So the partial with respect to x is 8yz minus lambda times 32x, set it equal to 0. Partial with respect to y, 8xz minus lambda times 8y, set it equal to 0. Partial with respect to z, 8xy minus lambda, 18z. And partial with respect to lambda is the opposite of 16x squared plus 4y squared plus 9z squared minus 144 equals 0. And that's the same as the constraint, essentially. Okay, I'm going to use my special way that I've taught you. Usually works, but not always. So solving for lambda, I get 8yz divided by 32x, but let's reduce to lowest terms. And after reducing, I get yz over 4x. Let's call this number 1. Solve for lambda again. I get 8xz over 8y. Reduce this to lowest terms. I get xz over y. Call it number 2. Do it again. Solve for lambda. I get 8xy over 18z. Reduce to lowest terms. I get 4xy over 9z. Call it number 3. Okay, time to start getting the variables in terms of x, my personal favorite. Okay. Let's set number 1 lambda equal to number 2. Lambda has to be equal to itself. Lambda has to equal lambda. So yz over 4x had better be equal to xz over y. Be careful, this is a little tricky. You think it's going to look like the other ones? No, that's why I put it in my lecture notes. It's going to be different. I'm going to multiply both sides of the equation by 4xy in order to clear fractions. Okay, and then reduce. The y's cancel over here, and on the left, the x's cancel. So on the left, I'm going to have 4y squared z over 4. The 4's cancel, that's nice. Over here, I'm going to have 4x squared z. So what do I have? I have y squared z is equal to 4x squared z. Well, assuming z is non-zero, divide out by z. So you get rid of him. And then I get y squared is equal to 4x squared. Well, now you're going to square root both sides, but what do you have to remember?
Plus or minus.
You know I'm going to test you on this. You had it on the quiz you just took, believe it or not. So I hope that you remembered it. So y is going to be plus or minus, oops, I already tried to reduce my square root of 4x squared. And then when you make this simplified, you get y is equal to plus or minus 2x. Save that for later. Now what? Let's set the first lambda equal to the third lambda. You know, lambda has to equal lambda. Here we go. I got yz over 4x had better be equal to 4xy all over 9z. Let's clear fractions. Multiply both the sides of the equation by 9z and 4x and hope for the best. Reducing. Let's see, I got my 9's canceling here, and I got my z's canceling here. All right. And then on this side, I got 4x's canceling. So what do I have? Yeah. That's pretty bad. I got 9yz squared. That's the left. I got 16x squared y on the right. Okay, I'm going to try to get z in terms of x. Divide out by y, assuming it's non-zero. And then I have 9z squared is equal to 16x squared. And if I divide both sides by 9, I get z squared is 16/9 x squared. And then you know, take the square root of both sides of the equation. And let's see, it turns out 16 and 9 are perfect squares. Nice. So this is going to reduce to plus or minus 4/3 x. Okay, now what? We substitute into the constraint, keeping x himself. Now, what is the constraint? We forgot. It was 16x squared plus 4y squared plus 9z squared equals 144. It was the ellipsoid, the egg. So when you substitute plus or minus 2x into y, and since y is getting squared, it doesn't matter plus or minus. Anytime you square positive or negative, it gives you the same. So that's kind of nice. So you're going to get 16x squared plus, and then you're going to get 16x squared for the second term. And then here you're going to get 9 times 16/9 x squared, but then the 9's cancel. Aha. So you get another 16x squared term. Add those together. Those are like terms. 48x squared equals 144. And then x squared equals 144 over 48. And then x is going to equal plus or minus the square root of 144 over 48. Now, you'll never guess. I wouldn't guess this. But 144 divided by 48 is actually a nice integer. Anybody know what that might be?
I'm gonna guess 3.
Yeah. So this reduces to plus or minus square root of 3. Cool beans. Now, since y is equal to plus or minus 2x, y is going to be plus or minus 2 square root of 3. And since z is equal to plus or minus 4/3 x, we have that z is plus or minus 4 square root of 3/3. Okay, now what? The question is, what are the critical points? Because look, in this problem, when you see that x and y are related by this plus or minus, and then z could be plus or minus, you get all kinds of options. One option is where everybody's positive. So one option is where you have a critical point would be positive square root of 3, positive 2 square root of 3, and positive 4 square root of 3/3. So that's one. But there are many others, folks. And it turns out, like if you have, let's say you had x being negative, and then y could be negative, but z could be plus or minus too. So what if he's positive? And I'm writing down all the max points because I'm going to write down the other critical points that are going to give you a minimum temp. Yeah, it's going to get pretty crazy here in a moment. What do I mean? I claim that there are 8 critical points. Oh my God, how did you know that? I'm just mixing and matching all the positive and negative choices. And I claim that when you plug them back into your temperature function, what was the temperature function? Boy, I forget. 8xyz. Look, if x is negative and y and z are positive, I hope you get that the temp will be overall negative. And if everybody's positive, x, y, and z, then the temp will be positive. If 2 of them are negative and one's positive, then you'll still have a positive because a negative times a negative is a positive. So I'm just writing down all the critical points that would give a positive temperature right here. These are all the critical points that would give a positive temp, where 2 are negative, all positive or 2 negative, and 1 positive. Oh, I'm missing one here. The one I'm missing would look like where the y and the z are negative. So those are all going to give a maximum. What is the maximum? Well, just plug it into your temp, and you'll get, 8 times square root of 3, 2 square root of 3, 4 square root of 3/3, and I claim that's 64 square root of 3, which is approximately 110.5 degrees Celsius. Oh, that's pretty hot on that temperature. Sounds like Mars. Now, what about the minimum temp? So there's more critical points. You got to be kidding me. No, I'm not kidding you. So what about it? Well, what if all 3 of the coordinates are negative? That'll make your temp negative. What if one's negative, but the other 2 are positive? That'll still give you a negative temp. So it's still going to give you a min. Here are all, I'm just listing them all out. All of the other critical points. And all of these give the same minimum temp. So the actual min temp is negative 64 square root of 3 degrees Celsius. That's all. There you go. I'm done with this example. So to recap, you create this big Lagrangian function of 4 variables, x, y, z, lambda. You take all 4 partials, you solve this crazy nonlinear system, and you get a critical point. In this case, since y could be plus or minus x and z could be plus or minus x, you get a whole mix and match plethora of critical points. And we want to if we wanted to maximize the temperature, and let's say they just wanted a max temperature, then you would just give it to them. Sometimes the problem might ask you for the critical points and the max value, or they may just ask you for the critical points only. So be very careful when you read the directions to one of these Lagrangian type problems, because they may ask you for something and you don't want to give them the wrong information. Now, full disclosure, I stole this problem out of my old calculus book when I was in high school, which is down here somewhere. I'll show it to you. Yeah, I kept it. I keep all my calculus books. So this book right here I'm showing you in the camera is by Swolkowski. Swolkowski is now dead, although his books are still, for legacy's sake, they're still out there. I think they're probably in their 50 millionth edition. But good things never go out of style. And this problem, when the way Swolkowski did it, they didn't list out all the critical points. They just said, what's the max temperature? Just give me the max temperature. So they didn't really care about all these critical points. But I re-engineered it for my purposes because I wanted you to see a possibility that you could get a lot of critical points, and you have to be careful. You plug in those coordinates to find out who gives your max and who gives your min. That's sort of the point. Okay. So I'm going to go over one extra thing and one other problem, and then I'll finish for the day. And this is important because this is finding distance, and then I'll finish Lagrangian next time. Okay, but distance is really important. You know, when you're working in 3D, we already know a few distance formulas. You know how to find the distance between 2 points. That's just the distance formula, which we're actually going to use here. You also know how to find the distance between a point and a plane. That involves the dot product. You know how to find the distance between a point and a line. That involved the cross product. Now, there's another way to do it, but I didn't show it to you. If you're really interested, let me know, because it does involve projections, but it's kind of cool. You got to know distances. So in this last example of the day, we're going to use Lagrange to determine a point that's on this sphere, and this is a sphere, centered at the origin of radius 2, that's furthest away from this point, 1, -1, 1. And then once we get the point, actually find that maximum distance. So we want to get as far away from that point as possible. That's the plan. We're going to use the distance formula. So here we go. Distance formula between some arbitrary point x, y, z, which that's the unknowns. We've got to get the coordinates of that unknown point. And we want to maximize the distance from that point to this given point. Oh my goodness. So folks, this is the function that you would have to do calculus on. This is the big fxyz. But I don't like radicals, because anytime you have to take the derivative of a radical function, it gets kind of messy. So here's the claim, and listen up, because if you do a distance problem and you don't do it this way, because you like pain and you end up leaving the radical in there, I won't even grade it. How this go? Why are you doing this to yourself and to me? The claim is maximizing a radical function like this d right here will be the same as maximizing what's under the radical. The radicand, in other words. So what are we saying? We're saying that we're going to throw off the radical. Now we'll bring it back into the conversation at the very end when we get the actual maximum distance. But I claim that the function that's underneath the radical, if we maximize that, of course we'll maximize the square root of it too. So we're going to maximize this big fxyz, which is the stuff that's under the radical. And that way we won't have to worry about having to use the chain rule when we take our partials, okay? Now, what's the constraint? You know, the constraint is the sphere. So this is definitely a candidate for Lagrange. We got our constraint, we got our function to be optimized. So our big Lagrangian of a function here is going to be this radicand. I'm just going to copy it down again. Minus lambda times the constraint, where you write the constraint where you subtract 4 from both sides, because you like to get it written as everything equal to 0. Now let's go get the 4 partials for this Lagrangian. Now I am going to have to use the chain rule, but at least I won't have to use the chain rule, like double chain rule with the radical. So when I take the derivative with respect to x of that first term, using the chain rule from calculus 1, it's 2 times the quantity x minus 1 to the 1 power times the derivative of x minus 1, but that's just 1. And then minus lambda times 2x. That equals 0. And I'm going to solve it for lambda while I'm here. I claim that lambda after reducing will end up being 2x minus 1 over 2x, but the 2's just cancel. So it's just going to be x minus 1 over x. Okay. When I take the partial with respect to y, I get 2 times the quantity y plus 1 minus lambda times 2y, set that equal to 0. If I solve for lambda for this one, I'll get, and reduce, I'll get lambda as y plus 1 over y. Take the partial with respect to z, 2 times the quantity z minus 1 minus lambda times 2z, set that equal to 0. Solve for lambda, I get z minus 1 over z. And of course, when you take the derivative with respect to the Lagrange multiplier, lambda, you'll get opposite of your constraint. And when you set it equal to 0, that is your constraint. Okay, now what? I got 3 different lambdas. Let's set the first one equal to the second one. So if I go x minus 1 over x is equal to y plus 1 over y. So this is setting the first one equal to the second one. If I multiply both sides of the equation by xy to clear fractions and then reduce, and then distribute to get rid of parentheses, and then subtract xy from both sides so the xy goes away. Now, this is where students screw up, especially after seeing my last problem. Do you notice when I solve for y, I get y equals negative x, not y could be plus or minus x. This is very different. Please be careful and don't confuse this with y could be plus or minus x. Here it's saying y has to be the opposite in sign of x, not plus or minus. So that's going to be very restrictive. When I set the first lambda equal to the third lambda to try to get z in terms of x, I'm having x minus 1 over x equals z minus 1 over z. Multiply both sides of the equation by xz to clear fractions. Then I get z times x minus 1 is equal to z minus 1 times x. Distribute to get rid of parentheses. Subtract xz from both sides. That kills off the xz term. I get negative z is equal to negative x. Multiply both sides by negative 1, and z is just simply x. Not plus or minus. Do not do that. Know the distinction. It's these subtleties that separate a good student from a great student. Okay? So I'm going to plug z equals x and y equals negative x into the constraint equation. That's the sphere. Okay? So I'm going to have x squared plus negative x squared plus x squared equals 4. Well, negative x squared is still positive x squared. It gives you the same result. And then when I add all the like terms on the left-hand side, I get 3x squared is equal to 4. X squared is 4/3. You know, I'm going to square root both sides. So don't forget your plus or minus. Oh, so x can be plus or minus. I'm going to simplify this a little bit. 2 over square root of 3. Does that mean y could be plus or minus? No, no, no. This is where you're going to screw up. So what do you get? Let's say we choose x to be the positive 2 over square root of 3. Since y has to be the opposite in sign, not plus or minus, and z has to be what? Exactly what x is. So whatever x is doing, z has to do it. That's a critical point. Another critical point, if x is negative, y will be opposite in sign, and z has to do whatever x is doing. So these are 2 critical points only. Now, do any of these give a max or a min? And how the heck do you tell? Because there's no such thing as a d-test when you're doing Lagrange. You do it by trial and error. I'm not kidding you. Like, plug this into your fxyz, you know, and so it turns out that the one that gives the max distance is this one, and you can try it. So when you do like square root of negative 2 square root of 3 minus 1 squared plus 2 over square root of 3 plus 1 squared plus negative 2 over square root of 3 minus 1 squared, this gives you a max distance, and this is 3.73. What about the other critical point? Does anybody care about him? Yeah, he will give you a min distance essentially. Okay. If you were looking. So that concludes that problem. I know it seems a little hokey that the way you distinguish between the max and the min is you plug it into the function to be optimized and figure out, well, what makes him bigger, what makes him smaller, but that's the way you roll. But it is pretty cool though, no d-test. And that concludes that example.